Good morning. Welcome to the 11th session of the course Digital Electronics. In this chapter, that is Digital Principles, we deal with number system and different types of conversions, that is binary to decimal conversion, binary to hexadecimal conversion, and hexadecimal to decimal conversion. So, while to deal with different conversions, first we have to know what is a number system. A number system, it is defined as a system of writing or expressing numbers. It's a system to express numbers. So we can define it as also it's a mathematical notation for representing numbers using a given set of digits or a set of symbols. Okay, when I say it using a given set of digits, in decimal we use digits 0 to 9. These can be also called as symbols. If you use these digits or symbols in a consistent manner, that becomes a number system. In daily life or in day-to-day correspondence, we use decimal system. So, how does the value of a digit in a number depends? It depends on the digit itself. Like if I say 0 and 9, the two digits, digit 9 is greater than 0, we all know. So, the value of any digit in a number is dependent on the digit itself. Then, its position in the number. Like, consider an example of 250 and 25. Okay, the value of 2 in 250 is 200 because its position is in 100th place, and in 25 the value of 2 is 20. So the value of any digit depends on the digit and its position in the number also. Okay, then the base of the number system. In the previous example what I had taken, the base of the number system was decimal. Okay, it was base 10 system. So we have many other number systems in which the value of any digit depends on the digit, its position, and the base also. So what are the different types of number systems? The first we all are familiar with, it is base 10 system. The second is a binary number system where the base is 2. Then we have octal number system with base 8 and hexadecimal number system with base 16. Okay. In decimal number system, that is, we can also call it as base 10 system, we use 10 symbols or 10 digits. So what are all the digits? These range from 0, 1, 2, 3 up to 9. Since we are using 10 symbols, it is called as base 10 system. Okay. The next thing, binary number system. In binary number system, we use 2 digits. Okay. We use only 2 digits or 2 symbols. The 2 digits are 0 and 1. To express any number, we use only these 2 digits. Hence, it is called as base 2 system. The third one is octal number system. In octal number system, it is also called as base 8 system. So here we use 8 symbols or 8 digits. 8 symbols in the sense we use digits ranging from 0, 1, 2, 3 up to 7. Okay, from 0 to 7 digits are used. 0 to 7 symbols are used. Hence it is called as base 8 system. The symbols are 0, 1, 2, 3, 4, 5, 6 and 7. The next is hexadecimal number system. It is also called as base 16 number system. When we are using microcomputers and microprocessors, this is a very popular number system. It is called as base 16 number system or hexadecimal. Hexadecimal means 16. Here we are using 16 symbols. So what are all the 16 symbols? Starting from 0 up to 9, we have 10 symbols. 0, 1, 2, 3 up to 9, we have 10. Then from after 9, we have another 6 symbols, that is A, B, C, D, E and F. Okay, from 0 to 9 and A to F, we use 16 symbols to represent numbers in hexadecimal number system. So the first thing is, first conversion what we'll be looking into is binary to decimal conversion. Okay, most of the digital equipments or most of the computers, they work with binary data. They cannot understand decimal data. But we human beings can understand only decimal values. So while working with digital equipment, we have to convert binary code to decimal numbers. So this binary number is a weighted number. You have learned in previous classes of this chapter. This binary number is a weighted number. Weighted in the sense every digit has its own weight depending on its position. Depending on the position, every digit has its own weight. Okay. The decimal value of any binary number, how can we find it? It can be found by adding the weights of all the bits that are 1. By adding the weights of all the bits that are 1 and discarding the weights of all the bits that are 0. How can we find the value of any decimal number? Any binary number? Value of binary number, that is the decimal equivalent of any binary number, can be found by adding the weights of all the bits that are 1 and discarding all the weights that are 0. Okay, let's take an example. I have considered an example. Let's take a number, binary number 1010 and convert it into decimal. First, I have written the binary number here as 1010. Above that, I have mentioned the weights. So, the weights are, how can we identify the weights of binary digits? It is starting from LSB towards MSB. Starting from least significant bit towards the most significant bit. The power raises from 0 to n minus 1, where n is the number of bits in the binary number. Here 1010, this binary number has 4 bits and the powers range from 2 to the power 0 to 2 to the power 3. That is 4 minus 1 is 3. So 2 power 0 ಇಂದ ಹಿಡಿದು 2 power 3 ವರೆಗೂ LSB ಇಂದ MSB ವರೆಗೆ. That is from right to left. It goes on increasing. The power goes on increasing. Okay. If we take the decimal value of these powers, these binary weights, it becomes 1, 2 raised to the power is 1, 2 raised to the power 2, 1 is 2, 2 raised to the power 2 is 4, 2 raised to the power 3 is 8. Okay. What I told you, by adding the weight of binary ones, the bits that are ones, and by discarding the weight of digits that are zeros. So I'll be adding here 8 plus 2, that will give me the answer as 10. So the decimal equivalent of 1010 is 10 in decimal. Binary 1010 is equal to decimal 10. I can convert binary to decimal in another way. Like here I am multiplying each binary digit by its weight and taking the sum of products. I am multiplying each binary digit by its weight and taking the sum of products. So that will give me the same answer as the previous method, that is 10. Okay. Here I have multiplied 1. Here I have considered the same number. 1 multiplied by 2 raised to the power 3 plus 0 multiplied by 2 raised to the power 2 plus 1 multiplied by 2 raised to the power 1 and 0 multiplied by 2 raised to the power 0. If I take the sum of these products, the final answer is 1, which is similar to the previous method what we did. Let's take another example. Okay. Here the example what I have taken is 11100. What I have done is I have multiplied each binary bit with its weight. Okay, and then I have taken the sum of all these products and I have got the answer as 28. Okay, how to find out the weights of each binary bit? That is from LSB, that is 0. I am multiplying each binary bit by its weight, that is 2 raised to the power up to 2 raised to the power n minus 1, where n is the number of bits. So in this problem I have 5 bits. 5 minus 1 is 4. Starting from 2 to the power 0 up to 2 to the power 4, I am multiplying each bit by its corresponding weight. If I look into the answer, it is 28. So how till now we explained how to convert a integer binary number into its decimal form. Now I will be explaining how to convert a binary fraction to decimal. Okay, how to convert a binary fraction to decimal. Here the number what I have taken is 0.101. I have to convert this binary number to decimal. How to do that? By multiplying each digit, okay, by multiplying each digit by 2 to the power minus 1, 2 power minus 2, 2 power minus 3 and so on. So the first, how to start and where to start? The starting point will be the first bit after the decimal point. I have to start with the first bit after the decimal point, and the weight of this position will be 2 raised to the power minus 1. It will be, the next will be 2 to the power minus 2, the next is 2 power minus 3 and it goes on like that. Okay, the number what I have considered here is 1.101. So if I multiply these by 1 into 2 to the power minus 1, 0 into 2 to the power minus 2, 1 into 2 to the power minus 3, then I will get the value as 0.5 plus 0 plus 0.125, that is equal to 0.625. Let's take another example. This number consists of the integer part and the fraction part. Okay, in the integer part I have written the binary weights correspondingly, and in the fraction part also I have written the weights. In the integer part it ranges starting from LSB towards MSB, it ranges from 2 to the power 0 to 2 to the power n minus 1, and in the fraction part it starts from 2 to the power minus 1 and then minus 2 and it goes on. Okay, so here the answer I have got is 4 plus 1, that is 5, and in the integer part it is 0.625. Okay, the total value is 5.625. Let's take another example. Here the integer part has 4 bits, so the weight ranges from 2 power 0 to 2 to the power 3, and in the fraction part I have only 2 bits. Okay, it is 2 to the power minus 1 and minus 2, the weights. If I add the binary bits, the weights of the binary bits that are 1, okay, 8 plus 4 plus 1, that is 13. I'll be getting as integer part, and in the fractional part only one digit is binary 1, so it is 2 to the power 1 into 2 to the power minus 1 is 0.5. That is, the final answer is 13.5. The next type of conversion is binary to hexadecimal conversion. Okay, when we deal with microcomputers and microprocessors, they mainly use hexadecimal values. So we need to have this binary to hexadecimal conversion if the system demands. Okay, how to do this? This is very easy. Like, first we have to group the binary numbers in group of 4 bits. We have to group the binary numbers in group of 4 bits starting from LSB, that is least significant bit, and we have to move towards most significant bit for the integer part. Okay, and then these group of 4 bits, they are replaced by its hexadecimal representation. The group of these 4 bits are replaced by hexadecimal representation. Okay, in the end, if the group is short of 2 bits, 3 bits, or if the group is an incomplete one in terms of 4 bits, then you can add number of zeros required to complete a 4-bit group. Zeros can be added as required to complete a 4-bit group. And for the fractional part also, the above procedure is repeated. Then the starting point is the first bit next to the binary decimal point. The first bit next to the decimal point or binary point, and we have to move towards right. Let's take an example. Okay, you can see here 1010, 1011, 1001. This is a binary number. I have to convert it into hexadecimal number. For that, what I should do is, starting from LSB, that is this one, moving towards left or moving towards most significant bit, I have made these binary bits in group of 4 bits: 1001, 1101, 0101. Okay, this is a 12-bit binary number, and what I got is 3 groups of 4 bits. Okay, and then I have replaced these binary bits by its hexadecimal representation. Like 1001 is represented as 9 in hexadecimal, 1011 is represented as B in hexadecimal. B means 8 plus 2 plus 1, that is 11. 11 is represented as D. 1010, 8 plus 2 is 10. It is represented as A in hexadecimal. The equivalent value is A, B and AB9. Equivalent hexadecimal value for this number is AB9. Next, I have taken another example. Okay, this is a 10-bit number, 10-bit binary number. I have to convert this into hexadecimal. So the procedure is similar. Starting from LSB, I am making a group of 4 bits towards MSB. Like 1111 is the first group. Then we have 1011. Last, I am in the end, I have only 2 binary bits, that is 10. In the end, I have only 2 bits, that is 10. So I am adding 2 binary bits to complete the 4-bit group. Here I am adding 2 binary bits to complete the last group of 4 bits. So now I have to write the equivalent hexadecimal representation. 0010 is represented as 2, 1011 is represented as B, that is 8 plus 2, 10, 10 plus 1, 11, 11 is represented as B, 1111 is represented as F in hexadecimal. So the hexadecimal equivalent is 2BF. I have taken an example with the integer part and the fractional part in this one. 1010.0111. Okay, this has to be converted into hexadecimal. How to do this? Like in the integer part, we have a group of 4 bits. Okay, 1010, that is 10, equal to A in hexadecimal. And in the fractional part, 0111, that can be grouped as 4 bits, and it is equal to 7. This is equal to A7. Next, we have one more example. In this example, you can notice that I'll be adding 2 more bits to complete the 2 more bits to complete the 4-bit group. That is 10.100. Okay, I have told you while explaining the conversion that you can add zeros as and when required. Okay, the integer part is 10, that is it is having only 2 bits. So to complete the 4-bit group, I am adding 2 zeros. It is 0010, that is 2.100. I am adding one more 0 here to complete the 4-bit group. So this becomes 8. The answer is 2.8 in hexadecimal. Okay. The next conversion is hexadecimal to decimal conversion. How can we do this? A hexadecimal number can be converted into its decimal equivalent by multiplying each hexadecimal digit by its weight and then taking the sum of these products. The weights of hexadecimal number are increasing powers of 16 starting from right to left. Okay. This is similar to binary to decimal conversion. What we did there, we were multiplying each digit by 2 raised to the power 0 to n minus 1. Here we are multiplying each digit by 16 raised to the power up to 16 raised to the power n minus 1. Okay. Here the number what I have taken is E6C1 hexadecimal to decimal. Okay. E is starting from LSB, that is 1 is multiplied by 16 raised to the power 0. C is multiplied by 16 raised to the power 1. 6 is multiplied by 16 raised to the power 2, and E is multiplied by 16 raised to the power 3. Okay. If we multiply these individual numbers by its weight and then if we add these products, I'll be getting the final value as this. Okay. Here E is written as 14. Hexadecimal E is equal to 14 in decimal. 14 multiplied by 16 to the power 3 plus 6 multiplied by 16 to the power 2 plus C is written as 12 multiplied by 16 to the power 1 and 1 is multiplied by 16 to the power 0. Okay, the final answer is 59,073. Let's take another example. Okay, the example what I have taken, the number what I have taken is A85 hexadecimal to decimal. I am converting A85 into decimal. Starting from LSB, that is 5 multiplied by 16 power 0, 8 multiplied by 16 to the power 1, A multiplied by 16 to the power 2. So this A is written as 10 in decimal, 10 into 16 square plus 8 into 16 to the power 1 plus 5 into 16 to the power 0. If I add these products, the value what I'll be getting is 2693. I have taken one more example with the fractional part. Okay, this is 5A.12 hexadecimal to decimal. From LSB towards MSB. Okay, from LSB towards MSB, we have to multiply the digit, hexadecimal digit, by its weight. Okay, A is multiplied by 16 to the power 0 and 5 is multiplied by 16 to the power 1. This is for the integer part. For the fractional part, this 1 is multiplied by, after the decimal point, I should start by the bit after the decimal point, that is 1 is multiplied by 16 to the power minus 1 and this 2 is multiplied by 16 to the power minus 2. So the answer what I have got is 90.073125. I have given you few exercises, a lot of exercises which you can practice and be confident in these conversions. So to convert binary numbers to their decimal equivalents, we have given around 10 problems which you can solve and practice. To convert binary numbers to their hexadecimal equivalents, I have given many exercises. This also you can practice. To convert hexadecimal numbers to their decimal equivalents, I have given around 10 sums, 10 problems which you can practice and okay. Now after completing this session, before completing this session, let's check out what we have learned by solving a few multi-choice questions. Okay, the decimal equivalent of binary 10101 is, now we have learned how to convert binary to decimal by multiplying each binary bit by its weight and taking the sum of products. Okay, if we do that, I'll get the answer as 21. Okay, I'll get the answer as 21. The right choice is B. The next question is, hexadecimal number system uses dash symbols. How many symbols are used in hexadecimal number system? I have told you we use 16 symbols. Okay, that is 0 to 9 and then A to F, 0 to 9 and A to F, total 16 symbols, 0, 1, 2, 3 up to 9, A, B, C, D, E, F, total 16 symbols we use. Okay, next is decimal equivalent of hexadecimal number 86. Okay, how can I get this number, get this value? 8 into 16 to the power 2 plus 6 into 16 to the power 0. The answer is 134. Okay. Next question is the radix for octal number system. The radix for octal number system is 8. It is base 8 system. The base or radix is given as 8 in octal system. The answer is B. The decimal equivalent of 1111.10 is the decimal equivalent of this number. Okay. What we get is question number 5. The answer is 15.5. 8421. The weights are 8421. 8 plus 4 plus 2 plus 1. I get the integer part as 15 and 0.10 is 1 into 2 to the power minus 1. So it is 15.5. The next question. Hexadecimal equivalent of binary 1111 is F. Binary 1111 is represented as F in hexadecimal. Okay. The next question. hexadecimal equivalent of this binary number. How can I represent? I have to make group of 4 bits starting from LSB towards MSB. If I take these two groups, the answer is DA. 1101 is D, 1010 is A. The answer is A. The radix for hexadecimal system is, radix is nothing but base. Base of hexadecimal system is 16. The answer is D. The radix for binary system. Okay. The next question. The radix for binary system is 2. The answer is B. The final question, what we have in today's session, the radix for decimal number system. Okay, radix for decimal number system. This decimal number system is also called as base 10 system. The answer is C. For these digital principles, these binary to decimal and binary to hexadecimal conversions, you can refer the books Digital Electronics Principles by Tokyo, Digital Fundamentals by Floyd, or Principles of Electronics by V.K. Mehta and Rohit Mehta for further study. Thank you. Hope you enjoyed this session. Happy learning. Thank you.